Hello, everyone, and welcome to phyloseminar.org, a project supported by the Society of Systematic Biologists. The next three talks are going to be on the theme of bias sampling in phylogenetics. What does it do to our inferences, and what can we do about it? Today's talk is going to be a theoretical perspective from probabilist Leah Popovic. The next talk will be from Vladimir Minin concerning a new model that explicitly accounts for preferential sampling, and then Nicola Di Maio, who will discuss the sensitivity of discrete trait models to sampling strategy. As I mentioned, today we have a talk from Leah Popovic. Leah has her PhD in statistics from UC Berkeley, where she worked with probabilist David Aldous. She then did a postdoc at the University of Minnesota and then another at Cornell. After that, she took a faculty position at Concordia University, where she has been since 2007. In addition to work on microevolutionary models in the tree of life, she works on probabilistic analysis of chemical reaction networks. Welcome, Leah, and I'm looking forward to your talk.
Thank you, and thanks for the invitation to give a talk in the Philo seminar. My talk is titled Ancestral Features in Trees with Trait-Dependent Diversification, and most of the work is done with my former PhD student, Popovic Rivas. And it's based on some extension of my work on modeling coalescence for macroevolutionary trees from a number of years before with my former advisor, David Aldous, and then with my French colleague, Amaury Lambert. So I'm going to start by trying to motivate what made me look at phylogenies for processes with state-dependent traits and try to explain the problem. And just to sort of go back about 20 years, at least, to sort of say the premise of the whole problem is that once one has molecular phylogenies based on extant taxa, one is typically, the evolutionary biologists are interested in also inferring speciation and extinction rates that gave rise to the species in that phylogeny. And it's over the years there have been a number of inferences, mostly based on assumptions about constancy of rates of the diversification rates through time and across lineages. So if one assumes that the rates are constant across time and they're constant for all different species, then one can make likelihood calculations about given certain birth and death rates for the process. In other words, given speciation and extinction rates in the tree, what is the likelihood that that phylogenetic tree actually, came about? And the reason why this can be done is that essentially the shape of the phylogeny is influenced by both, in essence, both of these parameters, whether one uses them specifically as speciation or birth rates or extinction and death rates, or one uses the net rate, which is the difference between birth and death rates, plus the ratio of extinction to speciation. One can see that both of these parameters definitely affect the shape of the phylogeny, and the likelihood calculation depends on both of these parameters. Unfortunately, studies have shown that heterogeneity in species richness cannot be explained by processes with homogeneous diversification rates. And furthermore, Roboski in a couple of his papers showed that even if one simulates a tree with even modest levels of heterogeneity in speciation rates, they will result in a consistent, and then one tries to infer the diversification rates based on an assumption of their constancy through time and lineages. This will result in a consistent positive bias in the estimates for extinction rates. And this will particularly be exacerbated by phylogenetic tree size. So already at some point, about, I would 5, 8 years ago, people have started looking at possibly calculating likelihoods using somewhat different assumptions. So if one starts off with saying, okay, what gave rise to this phylogeny is a process with heterogeneous diversification rates, then the scientific question is, how do you uncover which traits possibly affected the diversification rates? Whether these are, so there are various sort of hypotheses, whether these were ecological or geographic or other kinds of traits. But from the statistical point of view or the mathematical point of view, what one definitely needed is new sort of likelihood methods, new simulation methods. And starting in 2006 and sort of going on with a number of papers, 2000 until pretty much a year ago, people have devised state-dependent speciation and extinction models. The first one was called BISSI, which stood for binary state speciation and extinction models, because it assumed that you were looking at a trait with two possible values. And then later on, a number of other simulation methods based on whether it was a quantitative trait or geographic trait were developed. And all of them essentially directly incorporated trait dependence into the birth and death rates for their process of evolution in order to calculate the likelihood that this kind of process has given rise to the tree with the current traits in the extant species. So this was sort of pretty exciting for a while, except that, randomness has a catch. And essentially, it's due to the fact that, the space of trees is extremely large, and many different factors can affect what kind of shapes and what kind of distribution of traits you see in the extant species. So as of about a year ago or so, people have noticed that there's serious problems with a specific review paper, which was quite good, by Goldberg and Roboski, discussed all of the problems with hypothesis testing based on these likelihood models. Essentially, model misspecification will lead to incorrect inferences. Type 1 error is quite large because there are other factors that can lead to a specific kind of phylogeny, and it's not due to the state-dependent traits at all, or the rates that depend on the trait in question. They could be just completely other stochastic factors. And so, sort of, I'm assuming that this has sort of dampened some of the enthusiasm for using these likelihood models. But essentially, it is not the flaw of the modeling. It's more of the flaw that we need a better understanding of what kind of statistics for phylogenies would be helpful in these situations, and a better understanding of what kind of shapes on trees we get from processes that are more complicated than just neutral evolution. So I don't really have that much to say in terms of statistical inference, because as a probabilist, I sort of look at more of the stochastic properties of the models. And so my motivation for looking at this is to sort of see what kind of, there's a lot of literature about, the distribution of random trees, of edge lengths on the trees, of various other statistics on these phylogenies that are based on neutral evolution. However, there's very little done in terms of, there's some, high-level theoretical results on what multi-type branching processes do, but very little in terms of what that means in terms of affecting the shapes, and what kind of statistics are particularly useful for multi-type branching processes.
So yeah, if you don't mind, just so I understand this paper, I mean, I understand that you could reject some sort of model if there's some model misspecification, but are you saying that these techniques would infer that there was a positive association with just an arbitrary trait under model misspecification? I don't quite understand how that would be.
I think essentially what happens is the following. You assume you start with a given phylogeny, right? You start with a tree. Then you assume that you have some type of trait-dependent model of evolution on this tree, and you calculate and so you can say parameterize it, with a few, or typically what I've seen is, anywhere from 4 to 10 different parameters. And then you sort of you calculate the likelihood of this tree under the different models, you find the maximum likelihood parameters, and then you sort of test the hypothesis whether, some of those parameters are 0 or not, and so you sort of are trying to find the best model of those that you're considering. Unfortunately,
okay, I get it. It's the parameters really get you in trouble.
Well, to some extent, because what you're doing is you're essentially picking the best model among all those that you've just specified in terms of what kind of process you have. You're not including in the whole thing other possible factors that could have given rise to that particular phylogeny. Right, so you could have had, certain, because of the randomness in the size of the tree space, you could have a sort of, a phylogeny that looks somewhat funny because of completely different reasons and not because of the character association. So you will infer that there's a positive association, even though the trait might not have contributed at all to the shape of that phylogeny.
Got it. Thank you.
Okay, and so I should immediately say I apologize for going back and forth between branching process terminology and sort of evolutionary biology terminology, just because from this point on, a lot of my work, a lot of the results in the talk are based on sort of probabilistic results based on branching processes, where we start calling things individuals rather than species, and birth and death rates rather than speciation extinction. But hopefully that'll sort of be relatively straightforward to follow. So just as an example of a picture, so the idea is you can have, so there are two things that I just wanted to stress. There's a process, evolutionary process, that gives rise to a full tree. And those are the trees that one sees on the left-hand side here. And the top tree is sort of a one-type evolutionary process where there's no differentiation between the different types in terms of their rates. And then the bottom tree is a two-type process where one can see by the coloring of the nodes that some of the species are winged and some are not winged, and that might, so that each branching node is dependent on which type the parent node is of. So then both of these, so this would sort of be the model that one typically looks at in terms of neutral evolution, and these would be the models that one would have to use multi-type branching processes to analyze. Then, of course, phylogenies don't typically, unless one includes fossils, don't typically include extinct species, and those are the ones I focus on, where one is basing all the inference on extant species. So once one prunes off the various extinct lineages, one gets a reduced tree or a phylogeny in both of these cases. So the mathematical processes that are appropriate, for modeling here are either discrete time processes, so multi-type Galton-Watson processes, or continuous time, which is much more common. But there are multi-type birth and death processes, meaning that the birth and the death rates both depend on the state of the parent. And then, of course, one goes forward in time and has a full ancestral tree, and then from it obtains the reduced phylogeny, as in the figure on the previous slide. And in the sort of the single type process, one can take advantage of a lot of sort of the inference and the modeling using a backwards coalescent process. And a lot of that has to do, and the reason why that can be done is that there's a certain, because there's a single type, there's a certain exchangeability in terms of the species and their randomness. So the same, the different species at present are exchangeable in the sense that one just picks a random pair in order to look at their most recent common ancestor and goes backwards in time that way. Unfortunately, in these multi-type processes, this is no longer an option because first of all, the different types are not exchangeable, clearly, because you have so first you have different types in the extant species, but second of all, even if you looked at the types that are, if you sort of classified them into two groups and tried to do some kind of coalescence back, you really cannot get a Markovian process back, because in order to figure out the time to coalescence, or the most recent common ancestor time for two species, you essentially would have to know or put a probability prior on the type of the parent. So one of the things that occurred to me then, that what would be useful is other kinds of constructions, which might take less time than sort of simulating forward as these BISI and other SSE models do. And one of these different types of coalescent constructions is sort of a horizontal, so a sort of a horizontal Markovian construction rather than vertical. And it happens that this can actually be extended to multi-type Galton-Watson processes, which is the next thing that I want to briefly discuss. So let's start off with just looking at what is a Galton-Watson tree. So in this case, in the multi-type setting, one starts off with a root ancestor, and then one has a pair of offspring distributions, so one for each possible type of the parent. And so one has depending on the type of the parent, one has a law for how many offspring of different types one can have. So in this case, mathematically, it doesn't really matter whether that one is using binary trees. So we've just generally presented it with possibility of having different size of offspring from 0 to infinity in the integers. So in this tree, then one can record just the branching process sizes, which will be a pair of number of individuals of different types. So in this picture, the first coordinate is the number of individuals in the different generations of type 1, and then the second coordinate is the number of individuals in that generation of type 2. Of course, one is not, there's lots of things that are known about just the population sizes for multi-type branching processes, but a lot less is known about the structure of the tree itself. So as I mentioned, there's a certain horizontal construction of a coalescent process for modeling the phylogeny of a branching process. And so I will first try to explain it just for a single type process, because the multi-type is essentially just an extension of this construction. So essentially imagine, one should imagine that the full ancestral tree is somehow embedded in a plane with various horizontal coordinates just being a consequence of this embedding in a plane, so that things don't, overlap, the edges don't overlap each other. Which way, this is of course which way one can flip it around, any kind of symmetry is fine. So this, which way it is embedded in the plane is irrelevant. So meaning which one is the leftmost spine of this tree is not really of importance. One can pick any one of the lineages from the root to the extant species. And then in a certain, under certain conditions, one can look at the spine of this tree. So if one then wants to prune off all of the extinct species, that will eliminate all of the edges that don't lead to the nodes that are present in this top level horizontally. And there's a way to sort of go along the spine at each point and just associate different random variables to each of the parents along the, or each of the nodes along the spine, then do a certain pruning procedure, which identifies there's a certain, under certain conditions, there's a certain amount of independence of how one picks these offspring distributions then along the parents in the ancestry. And then one can do some sort of pruning for that offspring distribution, which takes into account the probability of being extinct X generations later, where X is just given by the depth of this node in the spine in the tree. And then one can construct the offspring forward and then proceed onwards. So essentially, this is all based on going backwards along the spine, constructing the various edges off of it, and then proceeding one by one horizontally to do the same along any other thing that one could essentially call another sort of spine, or the lineage from some extant species back to the root. And then once one has such a construction, it is quite easy to get, well, it can, the law of the most recent common ancestral times is just the number of generations back between any two extant species, and it can be calculated from the various, from the offspring distribution for this branching process. And so, for example, here, it is clear from this embedding that for all of this species 1, 2, and 3, most recent common ancestor is in generation -1, and then for the individuals 6 and 1, the most recent common ancestor goes all the way back, and that is based on the fact that from this kind of construction, one will essentially have no individual in between, so no individual in between this, the first part of the spine and the sort of the 6th lineage in the spine, the lineage in the spine leading to number 6 up until the depth -6. So what is particularly nice about this construction, okay, so this, once one has pruned the various extinct lineages, then one just gets a typical phylogeny picture. The reason why we did this construction was also to show that one can do this whether the resulting tree is binary or not. So we took into account that one could have in the original tree multiple offspring at any given time, and hence that factor will remain in the phylogeny as well. But the particularly nice thing about, which is sort of shown in this picture by the fact that certain branch points have multiplicities. So the ones between 6 and 7 have only multiplicity 1, but the one between 6 and 10 or 6 and 8 has multiplicity 2. So what's particularly nice about this construction is that essentially this construction of these depths, or the most recent common ancestors between any two extant species, can be recovered from a fairly simple to simulate Markov chain. So there's a certain Markov chain that keeps track of these multiplicities, whose transition probabilities are very easy to give in terms of the original offspring distributions. And so once one has constructed this Markov chain of these multiplicities, then essentially the coalescence times are just given as the first time where any of these multiplicities are non-zero. So for instance, in the case of individuals 1 and 6, the first time, so all of the multiplicities between 1 and 6 in generations -1 through -5 are 0, because none of these individuals on the spine have things that connect to 6. So the first non-zero multiplicity will be given at level -6, and that is how one obtains the most recent common ancestor between individuals 1 and 6. So this construction can further then be extended to a multi-type construction.
Sorry,
because
multi-type,
yes.
can I just ask? So I mean that makes some sense when you're talking about a single spine, but I mean even just in this picture you're showing right now, there's sort of lots of different spines, and like it seemed to indicate before, there's sort of like subspines on spines, and so how do you go about sort of doing what you just described with a single spine with these different spines hanging around?
The convenient thing about this construction, or it's a particular feature of this kind of construction or embedding, is that all these subtrees end up being independent. So all of those that hang off of different nodes are independent of each other. So essentially one goes along the first spine and attaches all the different subtrees, and then you can investigate each subtree on its own, and you have its spine only until the point where it links to the original spine.
I see. Okay, a spine is just something you sort of define by a stretch of contiguous tree.
Yes. So you start off with, you pick the first spine in any which way, or if you've already embedded the tree, then in the leftmost way, and then you attach all the subtrees to it. And the particularly convenient thing is that you can do that separately for each one that is hanging off of the spine. Obviously, they all have different laws because there are different depths, but you hang off, they hang off independently, and then within each one of them, you consider only the portion, like in this one, for the lineage 6, you need to sort of do the spine decomposition only up until where it joins to the previous spine. So then when you come to, for instance, the one for individual 8, you would only do a spinal decomposition up until it links to the one before. So you would only look, yeah, okay. So now, so the catch with the multi-type thing, though, unfortunately, is that you have to make some assumptions. So you have some initial leftmost spine that you pin down in your embedded tree, and you have to sort of generate also, you have to calculate the types of the individuals along that spine. So that's sort of the major catch of doing it in the multi-type case, because without that, you cannot do any of this sort of attaching of the subtrees off of the spine. So once Well, once you have that, so once you're considering putting on the types along the spine, then you essentially just proceed in the same way as I explained before, except that now these, all of these subtrees that are hanging off that you're attaching independently are given in terms of the multi-type branching distribution. And this multi-type branching distribution, of course, now complicates matters only in the sense that you have to keep track of multiplicities for each type, and it's just sort of extra vector long notation and keeping track of it rather than any sort of new element in terms of the construction of things. So again, the same sort of horizontal Markovian structure holds, and one can write down a Markov chain, and one can write down the transition probabilities for all of these multiplicities in this tree based on now slightly more complicated offspring distribution, because now you sort of prune off differently for different types and you have to keep track of all of those things. Now, if you're just looking at so maybe I should do an example of how this is done. So you start off in, let's say we have a case of two types, with this type 1 being empty circles and type 2 being full circles. So if you put down some probability distribution for the types along the spine, then that's sort of your initial point for the Markov chain. And then for each looking back for each parent, you independently sample from a certain offspring distribution, which is that pruned distribution that I mentioned. So you see here that there was an original offspring distribution, and then some things are the shaded ones, and those are the ones that got pruned because of they lead to extinct lineages, and only the black ones remain because those are the ones that will lead to some extant individuals. So then one obtains all of these different values for the multiplicities there. And so, for instance, if one has attached an offspring here that has a bunch of other offspring, then certain ones of those, so that's the pruning procedure, certain of those are going to move forward, and certain of those that are marked with the X will belong to extinct lineages, and we don't have to model them anymore. And so then one moves onwards with modeling the spine of this individual 6 that way. And the one just proceeds to the right of this individual, which makes it convenient because one can write it down as a Markov chain in terms of horizontal indexing. Now, in this kind of tree, of course, one can look at two types of features. One can either look at all of the most recent, all of the coalescent times, or one can look at the coalescent times of only the same type of individuals. So for instance, in this tree, one can look at the depth at which the individuals of type 2 will meet. So in that case, one is not looking at the common ancestor of 3 and 4. And so one would only look at, for instance, 1, 2 individuals, 1, 2, and 3, or individuals 1, 2, 3, and 5, and 7, 8, 9, and 10, and find sort of the distribution of the depths for those individuals. So the reason why we looked at that is that we wanted to see what kind of properties of the initial sort of process lead to different sort of skewing of the laws for the depths. And one can then write completely the formula for these kinds of things. So one can write the complete law for the most recent common ancestor of the same type of individuals. And, it's sort of based on these generating functions, but they're actually not that complicated to implement in any sort of mathematical software. And then one can also look at the most recent common ancestor of all the individuals. which would essentially represent the coalescence times in the tree. And then one can look at, what properties of the particular effect of that type on that on its offspring has, in terms of saying, are the edge lengths longer, for instance, if you are of, say, type 1, than if you're of type 2, or if you're of type 1, then in general, if you don't know the type of the species. So you can sort of compare the laws of the edge lengths based on what is the original offspring distribution. And we get, in the paper that we wrote, we gave examples for some very simple two-type models just to showcase what one can see about the balance and imbalance of these kinds of trees. So of course, this can only be done if you have a fairly simple model, and it intuitively makes sense why you would have an imbalance of a certain kind, and that you can sort of convince yourself that, that this kind of the description of the shape actually makes sense relative to your offspring distribution. So some very asymmetric types are, for instance, individuals of type 1 give rise only to their own types, whereas the individuals of type 2 can give rise to both type 1 and type 2. And so it's very clear that, you will have certain different kind of bushiness stemming from type 1s than stemming from type 2s. So that sort of concludes this sort of first part of my talk, where I wanted to talk about going just what are the different methods one can use to describe the coalescent processes that are related to multi-type trees, which essentially means that you can embed any kind of, you can put in any kind of trait dependence in terms of dependence on the type, in specifying particularly its offspring distribution of that type versus the offspring distribution of the other type. So that's sort of that's the direction where one would go from a branching process to sort of constructing a phylogeny or a reduced tree for the process that gives rise to the extant species. And now the sort of the second part of the talk, I wanted to just talk a little bit about, can one sort of go backwards and use certain features or certain statistical features of the phylogeny to infer some of these parameters of the original branching process. So if you have the phylogeny, then what kind of statistics or what features of these multi-type phylogeny? So when I say multi-type phylogeny, I'm not going to assume that one knows all of the states in the history of the tree, but at least the states of the current species, and maybe looking at one generation back. So are there some statistics that will help us determine if we assume that a certain birth and death process, a birth and death process parameterized a certain way, gave rise to this phylogeny, can we actually infer the parameters of this process, in which statistics would actually be useful in this regard? So is there some kind of identifiability of the parameters of the process is the question. So in order to sort of do this, we went back to look at what do we know? Okay, what kind of phylogenetic trees will we get if we use multi-type processes as sort of, so what I'm talking about now is we want to look at only the process of the reduced tree. So is there some kind of simpler likelihood that can be written down without tracing all of the stuff that we talked about in the coalescent before? So for instance, in the single type process, in other words, in neutral evolution, one knows that all of these neutral processes will essentially give rise to a Yule tree, which is just the tree, the ancestral tree of a pure birth process. And this is essentially, again, a consequence of this exchangeability or the neutrality of evolution that I've mentioned before, and the observation goes back to David Aldous in 1996. And so then we looked at, clearly, say you have K types in your tree, there should be, or there could be, another process going forward, like the Yule process that is the case in the one-type process, which creates a phylogeny for the reduced tree in the multi-type case. So we started off by defining a multi-type Yule tree as a certain kind of birth process. So again, since we're talking about reduced trees or phylogenies, there will be no extinction because all of the extinct lineages will have been pruned already. So imagine that you have a certain birth process, where the parent of a certain type has different rates for giving birth to for species of other types, including its own. So we have a set of rates which specify the sort of the speciation of that parent type. And then there's also a set of rates which denote the switching of a type of species from sort of where it is as a parent to how it continues on. And I will try to explain in this picture of why we need these switching rates. So if one looks at for instance, of having simulated a multi-type birth and death process in this picture, this sort of, the picture number 2 is one that is sort of given an extant time right here, and it sort of has continued from this, going forward in time, has continued from developing from this tree to developing to this tree at this specific time t over here. And in this case, there's just a 2-type process. There's individuals that are marked with these dashed lines and the individuals that are marked with full lines. And, the dashed line individuals have their own birth rate for its own type of individual, and also for the individuals of the other type, and they have their own extinction rates, and the same goes for the other type. Now, if one then looks at the pruned tree from deleting all the extinct lineages in this tree cut off, with the extant time here, then several of these lineages where the parent didn't make it actually all the way to today may appear as a lineage that has switched its type from this parent type to the offspring type, because the offspring is the one that actually has a lineage that is extant. So this is where the switches arise, because some of the parents their lineages just don't make it to today. And so where they give birth to an offspring of a different type may appear as a switch in the history. So this is what creates then a phylogeny where, even without any splitting of nodes, you can have a node just switch its color in the next generation going forward. So this tree from the previous picture would then, in sort of a discrete setting, lead to a phylogeny that looks as the tree on the right-hand side in the slide, where one does have splits, but then one also has, and at the split, one can keep the parent keeps its character, its type, the offspring can be of the same or different type, but then one also along the lineages has these switches of types. So that's where, given any type, one has these two sets of rates, one for splitting rates and one set for the switching rates. And of course, it is clear that the shape of the tree will be affected by, if one has it'll be affected by what kind of splitting rates we assume, and the distribution of types of the extant trees and obviously along the tree will be affected by both of these things. And one can sort of show that this indeed is, if one starts off with a birth-death process of multiple types, as one does in this picture, that indeed this tree is the multi-type Yule tree that I described with these two sets of rate parameters here. One can show that it is indeed, this tree is indeed Markovian going forward and given in terms of this pure birth process plus switching. So then once one has this result, one can sort of then look at only these kind of multi-type Yule trees, and one can consider what are the useful statistics. So for the Yule trees, it is known that there are certain results about the distribution of cherries and of pendants in these trees. So that seems like a plausible thing to look at in this context, especially since here cherries and pendants have colorings and so may give a lot more information. So the useful statistics will be not just the leaf configurations, which is the number of different types at the present time, but also the cluster configuration, which is essentially looking, peeling a few layers back to the most recent common ancestor of any two consecutive species, and then giving the number of different multi-type cherries and pendants there. So I will explain a little bit what a cherry and a pendant is. A cherry is just a cluster of size 2. So in this tree in the right-hand picture, we have two cherries. This one on the left side and this smaller one on the right side. And then one also has pendants, which are leaves that are not part of a cherry because they attach to essentially another subtree as opposed to just another leaf. And once one puts types in this case, I've given a full listing of what happens when you have two different types in the tree, but one has clearly a certain combinatorial number of different types of cherries and k-squared different types of pendants. And then one can look at the statistics on these numbers and see whether this actually reflects the process that gave rise to the tree in a useful way. So that was our goal here in the next set of results, is that we wanted to look at, first of all, given these multi-type Yule trees, can one calculate the laws or the mean and variance of the number of cherries of different types and the mean and variance of the number of pendants of different types. So in discrete time, one would have a phylogenetic tree, or let me put it, in models where one is not yet concerned about edge lengths, one essentially looks at phylogenies with a fixed number of leaves, right, which we use n to sort of think of as here, and one can write down recursive equations for the whole vector of the mean number of cherries and for the mean number of pendants, and then sort of using Mathematica, one can calculate for any n what the means and the variance of different cherries and pendants are. Now, why should this possibly be useful? Because this one kind of also needs the law of the distribution of the number of of cherries and pendants based on the rate parameters. One can sort of start looking at what happens when the number of leaves is large. So if one then looks at asymptotic results as the number of leaves grows, one can obtain a sort of central limit type theorem result where that is similar, but not, it's more complicated than the result one has for a single type tree and the number of cherries in a single type tree. In this case, one has this result where the number of cherries and pendants minus the limiting mean divided by a certain normalizing factor goes to a vector valued normal distribution with a certain limiting variance, where sort of the reason why everything is vector valued is that you have this k choose 2 number of cherries in k squared number of pendants, so you put them all in one vector, and that's how you end up with sort of this covariance matrix, etc., for the limiting normal distribution. And much of this work relies on certain polio-Erm process representations for how one attaches different leaves based on these rates and gets these cherries and pendants. And so the only difference between standard these results and standard central limit theorem results is that this normalizing factor is not necessarily square root of n, but could be bigger and could be n log n, and all of that sort of depends on how these rates, how there's a big matrix where one puts in all of these rates of switching and splitting, and then one looks at the eigenvalues in the eigenvectors of the first and the second, so the largest and second largest eigenvalue and eigenvector of this matrix, and that can determine what kind of scaling one has. So these are sort of based on, these are results based on these Erm processes that were analyzed very thoroughly by Svante Janssen, I don't know, 5-10 years ago. So one way in which this can be useful, and one can see kind of intuitively how it makes sense, these results make sense, is one can now look at these asymptotic results and say, if I know the proportion of cherries in this tree of the different types, can I recover the rates of my birth and death process from this? And so, for instance, this slide presents one such corollary where it says, if you know, in the two-type process, if you know the 6 different the limiting proportions of or the proportions for large n of these different cherry types, then you can infer all of the rates for the process back. And it actually, it sort of, if one analyzes the formula, they're quite simple and they intuitively completely make sense in terms of what proportion of cherries one should obtain based on these rates. Then one can do the same thing if in continuous time, there's just some slight difference in terms of how, the mathematical tools that are being used, because now instead of going recursively in terms of adding a leaf at a time, now one has just an increment infinitesimally in time, and so essentially one gets a system of ordinary differential equations for the means and the variances of the different cherries and pendants. But one can also, again, then derive the asymptotics in terms of, so now this time is the time from the origin, and if this time is quite long, so now it no longer depends on the number of extant species, but on the time since the original ancestor. And so if that time since the original ancestor is large, then one can again write one gets a set of formula that one can invert. so as to infer the parameters from the number of cherries and pendants at the present time. So the point of this exercise was to show that these kinds of combinatorial objects like cherries and pendants are actually can be quite useful for inferring the parameters of the process that gave rise to the phylogeny, if, of course, under the assumption that there was a multi-type birth and death process that gave rise to it, and that either the time from the origin is relatively large or the number of extant species is relatively large. So that completes the sort of the going back from phylogeny to parameters portion of my talk, and I just wanted to sort of put up a slide where the last two papers of references. So the last two papers are the ones based on which the first part of the talk gives the construction of the coalescent point process, and the second paper is the one that discusses this inference based on the cherries and the pendants. And the earlier references are just things that have been mentioned in the talk in terms of prior probabilistic results on single type trees and neutral phylogenies. So thank you for your patience and listening to the talk.
Thank you very much. That was a very interesting talk, and I'm sort of amazed actually that we've had multi-type branching processes for rather a long time, right? But this is definitely some new results in that area.
Well, I think it's because it's a different set of problems. There are some elements of this that go back to things that are that have been well known. So as you mentioned, a lot of results for multi-type branching processes have been known since probably the 70s or so. A lot of them are collected in the sort of the classical books by Arthrea and May or Harris. So these asymptotic results were looked at, and it's just that in the past one was interested primarily in the population size process and what one can say about the population size process, but not as much in terms of what about the trees and what about the shapes of the trees, or what about the coalescence times in the trees, etc., that are formed in the history of this branching process. So the perspective is somewhat different today because one is interested in I presume just one didn't have as much a need for these objects before.
Yeah, for sure. So how far do you think this can go? If I wanted to implement a multi-type branching process prior in Beast or something like that, how far away are we from being able to do something like that?
Well, I think it's the implementation is not the problem here, unfortunately. So I think implementing things is probably something that's doable. I think the bigger problem is knowing whether what you're doing then is really giving you a reasonable result or not. So I think that's part of the lesson that was learned from these BISI and other state-dependent speciation extinction algorithms, is that you can implement the model assuming some multi-type birth and death process, and the question is, can you then make a reasonable conclusion about your data from that or not? Because you will be making a conclusion based on this model specification, And so if you honestly believe that that is reasonable or credible, then you can go ahead. But one needs to be careful again, because as in the case of, even single type trees, one has to be cautious about the variability of just the shape of trees and all of that. That is a huge factor in. So again, if given that you are okay with assuming a certain model, I think the implementation is not that far off.
Cool. Well, thank you very much. I really appreciate your being willing to give the talk, and that was quite an interesting introduction. I should remind folks that the next talk is February 8th from Vladimir Minin, who's going to be talking about preferential sampling through time when estimating changes in effective population sizes. So, great. So until next month.